Hello everyone, today we'll be doing a special video covering a couple of questions from the 6th term examination paper. If you have applied to Cambridge University to study mathematics, chances are you'll be asked to take the STEP exam. So actually there are 3 levels of exam. There is the Step 1, Step 2 and Step 3. But since 2021, Step 1 is no longer offered, so we are left with the Step 2 and Step 3 exam. So each exam consists of 12 questions. They are a combination of pure mathematics, mechanics, and probability / statistics question. And candidates are given 3 hours to choose 6 questions to answer. So in my spare time, I actually like to do step 3 exam questions because even though they are not olympiad mathematics question, they are actually very good tests of your fundamental skills and also your content mastery of the high school mathematics syllabus. So you understand what I mean when I go over the 2 example problems. So without further ado, let us take a look at 2 problems from last year's step 3 exam. So the first question is actually a calculus problem, but it is not the type of calculus problem you will normally find in your high school exam. So let's take a look at what it is. So we have this question. For non-negative integers a and b, let IAB denote the integral from 0 to pi of cosine to the power of a cosine bx dx. So show that for positive integers a and b, we have the following type of recurrence relation: IAB equals a over a plus b, IA minus 1, b minus 1. So as you can tell, it's already very different from the type of conventional calculus problem where you just evaluate integrals or compute differentials. So how do we do part 1? Well, firstly, okay, I just put down the integral here again. Now we notice we want to get a recurrence relation where the a has decreased. So we might think that actually doing some form of integration by parts might be useful, where we firstly we integrate this second term and then subsequently differentiate the first term. So indeed, let's try and do that. So we use integration by part. So the first term is kept, but the second term is integrated from 0 to pi over 2, and then we have minus. Now we differentiate the first term where cosine a differentiated is a cosine a minus 1 sine minus sine x. So we have the differentiated first term. This was the integrated second term. Okay, and indeed we see that yes, this gives us a desired a minus 1. So we seem to be making some form of progress. Okay, let's tidy up the terms a bit. So over here, the first term, we see that because a and b are positive integers, so notice that when x equals 0, we have sine bx is 0. And when x is pi over 2, cosine to the power ax is 0. So the first part is just 0. The second part I just tidy up by pulling out the a over b here, and then the minus sign cancel. So I have just a over b integral cosine to a minus 1 sine x and then sine bx. So very good, we have the cosine a minus 1 appearing, but we seem to have a whole bunch of random signs which not very useful at this moment. But then we realized that actually there is another way to get cosine a minus 1 directly from here. So what we do is we realize that actually we can pull out a copy of cosine x, and then we are just left with cosine a minus 1. So what I mean is specifically pull out a copy of x, yeah, cosine a minus 1 x, then cosine x, cosine bx. And now if we look at what we gotten before and what we got now, we realize that actually we have a trigonometric identity that can allow us to combine this sine x sine bx and cos x cos bx, and that can be a way for us to cause ourselves to get cosine b minus 1. So what I mean specifically is very good. We want to find a way to add these two. So let's multiply throughout this equation by a over b, a over b, a over b. So we have this expression here. And now we can add equation 1 to equation 2. We have 1 plus a over b of I. And now we have this integral where the cosine is here and then plus the sine part here. So very good. Now we can actually apply our trigonometric identity as we wanted. And yes, this is actually cosine b minus 1x. So we have found a way to actually move the b down to b minus 1. And indeed, the right hand side here is just a over b. I of a minus 1, b minus 1. So we are done. We just need to organize the coefficients. Here is a plus b over b. Here is a over b. So bring the coefficient across. We have a over a plus b on the right side. So a very interesting problem one where the calculus is applied indirectly, and it takes a bit of ingenuity to spot what you need to do. So hope this gives a starting flavor of what the step 3 type of questions are. So it's really very fascinating and I enjoy doing them. Okay, let's take a look at part 2. So we're supposed to prove by induction on n that for all non-negative integers n and m, we have the following. Integral cosine nx cosine n plus 2n plus 1 x is equal to this weird looking stuff with a lot of factorials. So I mean, this is actually a test of how you apply induction, and again, it's not those straightforward high school induction, but the same principles apply. So what we do is we first start by looking at the base case n equals 0, because induction on n, and n is non-negative integer, so base case n equals 0. What is the left hand side? The left hand side is basically this is 1, this is cosine 2n plus 1, so we have left hand side is this integral which we can evaluate directly. 1 over 2n plus 1 sine 2n plus 1 x evaluated from x equals 0 to pi over 2. Okay, so we can evaluate this directly. We see that when x equals 0, the sine term is 0. When x is pi over 2, this thing you can check very quickly is minus 1 to the m. So we have the whole thing evaluates to minus 1 to the m over 2m plus 1. Okay, and the right hand side, we can simply plug in n equals 0. So 2 to the power of 0, 0 factorial, these are 1. Then 2m factorial cancels 2m plus 1 factorial except the 2m plus 1. The m factorial cancels. So we have minus 1 to the m over 2m plus 1. So very good, the left hand side and the right hand side agree. So the base case is done, and now assume that the statement is true for n equals k minus 1, and we are going to prove the statement for n equals k. So this is just standard induction stuff. Left hand side, for n equals k, we write down what is the left hand side, and then we realize that okay, probably we want to apply part 1 in some way. So we notice that this thing can be written in the I formulation as ik and 2k plus 2m plus 1. And by using part 1, we can have a over a plus b, right? So this is k over 2k plus 2m plus 1. And then reduce the terms by 1, so k minus 1 and k plus 2m. Now, this is where we use the induction hypothesis. So I k minus 1, k plus 2m is actually the same as the left hand side, except where I decrement n into k minus 1. So this is k minus 1 here, and then k minus 1 plus 2m plus 1 is k plus 2m. So I can use the induction hypothesis by putting in the right side for the case n equals k minus 1. So I have this is the expression where I have n replaced by k minus 1 in all the locations. Here 2n is 2 times k minus 1 plus 2m plus 1, so I get 2k plus 2m minus 1. So basically just check. I plug in k minus 1, and now if I want to prove the statement for n equals k, I probably want to find a way to fudge this to make it look like the right hand side. So well, we see 2k plus 2m minus 1, we have 2k plus 2m plus 1. To get 2k plus 2m plus 1 factorial, we are missing 2k plus 2m. So I multiply by 2k plus 2m in the top and bottom. And now we can actually tidy things up. So firstly, minus 1 to the m is here. The k goes into the k minus 1 factorial. Sorry, this should be k factorial. The 2 goes into here, so you get 2 to the power k factorial. 2m factorial is 2m factorial. K plus m gets absorbed here, so it gets k plus m factorial. Then m factorial stays as m factorial. This factorial times 2k plus 2m times 2k plus 2m plus 1 gives 2k plus 2m plus 1 factorial. So indeed, we end up with the right hand side. So here's the interesting induction problem, and hope you enjoy question 1 so far. So indeed, this is a very interesting kind of calculus problems that also uses induction. Okay, Now we will take a look at a very interesting geometry problem, as well as actually is like complex numbers applied to geometry, which is also a technique that is sometimes used in Olympiad geometry. So this will be a interesting intersection area with what we are showing today and Olympiad mathematics. So for this question, let us take a look at what it is. So given distinct points A and B in a complex plane, the point GAB is defined to be the centroid of the triangle ABK, where K is the image of B under rotation about A through a clockwise angles of pi over 3. So we have basically A and B are points, and then AB is rotated 60 degrees to give the point K. So this line rotates 60 degrees is AK, and G is the centroid of this triangle. Okay, so for part 1, if A, B, and G are represented by the complex numbers A, B, and G, so that G is given by 1 over square root 3 omega A plus omega star B, where omega is e to the I pi over 6. Okay, so actually this is just a direct test of your complex numbers understanding. So firstly, we see that, well, by definition, Ka, the vector AK is given by the vector AB rotated clockwise 60 degrees, right? So K minus A, which is vector AK, is given by B minus A times e to the minus I pi over 3. The minus sign is because we are rotating clockwise instead of anti-clockwise, so clockwise by pi over 3. So rearranging, we have K, I just bring the A to the other side. And now I expand out what is e to the I pi over 3. I mean, looking at the 30, 60, 90 triangle, e to the minus I pi over 3 is cosine is half, and then minus sine I, so it's minus root 3 over 2 I. So I just collect the terms A minus half, so I have half A, and then minus A times minus root 3 over 2, so plus root 3 over 2A. B is just this thing, so half minus root 3 over 2IB. Okay, and then G is just the centroid, is 1/3 A plus B plus K, so I just substitute in. I take A plus K, this one increases by a copy of A, so it's 3 over 2 now instead of half. And then B also increases K here, the copy of B by 1, so instead of half is 3 over 2 now, minus root 3. Yeah, so this thing plus A plus B is just this. And then if I want to put it in the form required by the question, well, I just pull out a copy of square root 3 and put it inside. So this is now square root 3. This square root 3 disappears. This one square root 3, this square root 3 disappears. So I have this. And now we can very quickly just check that, yeah, omega is actually e to the I pi over 6, right? So it is this time is cosine is root 3 over 2, and then the sine of that angle is half. So this is omega, and this is omega star. Okay, so part 1 is relatively straightforward. Usually the interesting thing comes when you apply do applications in part 2 and 3. So for part 2, we are given the quadrilateral Q1 with vertices A, B, C, D in that order, quadrilateral Q2 with vertices GAB, GBC, GCD, GDA in that order. So using the result in part 1, show that Q1 is a parallelogram if and only if Q2 is a parallelogram. Okay, so this is quite interesting application, sort of like mini theorem already. Now, how do we do this? Well, obviously we should find a way to characterize a parallelogram. So we realize that a quadrilateral WXYZ is a parallelogram if and only if this vector WX is equal to the vector ZY. Yeah, you can show this quite easily. It's not just parallel, I'm talking about these two vectors are identical in length and direction. So if you join the head to head and tail to tail, you will end up closing up into a parallelogram. So WXYZ is a parallelogram if and only if X minus W equals Y minus Z. So this translates the geometry into a complex number type of algebra problem. So that gives us a way to use part 1. So the way we'll do it is, okay, so we know that Q2 is a parallelogram if and only if this thing is 0, right? So let's just see what happens if we start with this term and apply the expression in part 1 and see what we end up with. So we have this GBC minus GAB. I'm just going in the order that similar to the first statement, and we just blindly substitute in part 1, see what happens. So GBC, I mean, you just follow the indices A, B, right? So A, B here. So I just BC, I have BC, minus AB, I have minus A, minus B, minus CD, so minus C, minus D, plus DA, so plus D, plus A. Yeah, just substituting in. And now we realize that we can actually pull out a copy of omega minus omega star across, because we have omega minus omega star times B. Then minus omega plus omega star times A, so this is minus A. Same thing, minus omega C plus omega star C, so this is minus C here. And then omega D minus omega star D, so plus D here. So very good. Actually, we actually can even calculate what is omega minus omega star, because omega minus omega star is the root 3 over 2 plus half I. So then you minus root 3 over 2 minus half I, we get I. And this thing here can be written in this form. Oh, I'm sorry, this should be a minus. Apologies. So it's B minus A minus bracket of C minus D. So and then we realize that what is this thing? This thing is the equivalent condition for if it's equal to 0, if and only if ABCD is a parallelogram. So indeed, this thing is 0, or rather Q2 is parallelogram if and only if this thing is 0, if and only if this thing is 0, if and only if Q1 is a parallelogram. So there we have it for part 2. A bit of interesting complex number way to show parallelogram properties. Okay, and lastly, the highlight is actually part 3. So part 3, we are going to prove a theorem that may be familiar to some of you all. What we have is a triangle ABC, and then T2 has vertices GAB, GBC, and GCA. So basically, AB rotates 60 degrees, then the centroid, so this is GAB, and then BC rotate clockwise 60 degrees, then the centroid here is GBC, similarly this is GCA, so triangle 2 is the green triangle. So we are supposed to show that this green triangle is always an equilateral triangle. So some of you who are familiar with Olympiad geometry will recognize this as Napoleon's theorem. So we are actually going to prove Napoleon's theorem using complex numbers algebra. So a really cool application of complex numbers here. And the way we are going to show it is we are going to check whether GCA minus GAB, which is actually this line here, is it obtained by taking this vector rotated by 60 degrees. So if we can show this, we have just proven that one side is given by the other side rotated by 60 degrees, and therefore the whole thing is an equilateral triangle. Okay, so I mean just directly substitute in part 1. Firstly, the left hand side, I just substitute in part 1, 1 over square root 3, C plus A, so C plus A here, minus AB, so minus A minus B. Okay, I'll leave this here for now. And the right hand side, same thing, I substitute in omega square over square root 3, BC, so B plus C here, AB, so minus A minus B here. And okay, maybe we should put in the omega square. So to do this, we need a few facts. Firstly, omega is e to the I pi over 6, so omega cube is e to the I pi over 2, which is I. So the first term here, omega cube, is I. Now second, omega square omega star. Well, omega times omega star is the length of omega squared, which is 1. So omega star combines to 1, we are left with 1 copy of omega. Now same thing, omega cube here is I, so we have I here. Omega square omega star is omega. Okay, now we can simplify this further by combining the two terms involving B. So omega minus I is actually omega star, and because this is root 3 over 2 plus half I, minus I we get root 3 over 2 minus half I, so that's omega star. So that's the observation we need. Combining this is actually so this will give us omega minus omega star here. So now we look back at the left hand side above, we see that we have omega c minus omega star b minus omega star b, and here we can combine the two terms again using the third observation here to get omega star minus omega is minus I. So indeed now we have shown that the left hand side is equal to the right hand side. So indeed one side of the triangle is obtained by the other rotated by 60 degrees. So what do you think of this problem? I mean, this is the first time, I mean, I haven't really seen a proof of Napoleon's theorem before, but seeing this complex number proof is really something that is makes it look so easy. So hope you enjoy the problems we covered today from the STEP exam. If you like this video, please make sure to click the like button, subscribe, and share it with your friends and family. And if you actually want me to cover more problems from the STEP exam, especially the mechanics or statistics problems, please feel free to comment in the comment section below, and I will make sure to check them out and cover them in the next video. So thank you and see you soon.